Oh yeah.
We dim the light.
All right. Ours, the senior design project, was a solar-based power supply. It consists of our team members, my project manager, Amit, Ilyas, and myself, Shazeb, Ahmed. Our faculty supervisor was Dr. Kovic. Before we started this design, we started off with what problem we should research. The problem that we researched was leaking electricity. This is basically the small electricity that you keep something plugged in and you lose that kind of electricity on your electric bill. It comes a little higher. Microwaves, TVs, so your little cell phone charger that you leave in, and then you just come back, plug it in. That's leakage electricity. The American Council for an Energy Efficient Economy predicted 45 billion kilowatt hours were wasted by US households alone in just a year. So basically all US consumers, putting them together in 1 year, spent $3.5 billion on just leakage electricity. So based on this, we came up with a solar-based power supply that would reduce leakage electricity while also reducing that clutter of wires you would get near an extension cord. This solar-powered charger will also give you the mobility to move your charger around for other items, while also this helps for countries that have limited energy sources, like countries that have load shedding problems because of the enormous request for energy, and also for countries that don't have a sufficient power source to get that kind of energy. This also produces a renewable energy source, so always going green is a good thing. Our preliminary design in EC 492 was a solar-based cordless telephone. This consisted of 5 main components. We had a solar cell, a voltage booster, a voltage regulating circuit, a smart circuit, which would be our microcontroller, and also a 9-volt backup battery just in case the solar cell wouldn't be good enough. There was a problem with this design. The problem was that the indoor light intensity that we have in most households here, it wasn't strong enough, and most of the solar cells weren't efficient enough to create that. And we researched about 6 different solar cells to do that. So we refined our design to a solar-based charger. This solar-based charger did the same functions. It offered portability, it did less power consumption, there was a decrease in leakage electricity, and it charged many of your devices that charge by 5 volts. So our design flow for this certain design that we had starts off with the solar panel giving us 5 to 6 volts at 200 to 300 milliamps. Then it moves on to a battery charger and management circuit. From there, it'll move on to a lithium polymer battery, which will be charged from the input coming in from there and go to a switching circuit. This circuit here will decide if the lithium battery is charged. It'll move on to a voltage booster circuit to get the output at 5 volts consistently, going to an output to connect to any electronic device that takes 5 volts. If the lithium polymer battery was dead, a backup battery would kick in and do the same output. The lithium battery would be connected to a microcontroller, which will show an LCD. Basically, that LCD will display the voltage on that has the lithium battery and also the remaining time left on the battery. Our hardware consists of main components that we had on the cordless telephone. It consists of a solar cell, a battery management circuit, a voltage booster circuit, an automatic backup battery switching circuit, and a microcontroller. We used the PIC in this case. The 6 different solar cells we tested, 3 of them weren't sufficient enough at all. So the 3 main ones that we went for were the amorphous solar cell, the photovoltaic, and the monocrystalline. We ended up choosing the monocrystalline due to its durability, its waterproof properties, and also its dimensions and weight were very well, and the substrate type was perfect for our conditions. And to explain the hardware of our circuitry, I'll move it on to our project manager, Mr. Amit.
Good afternoon, everybody. So our core of our whole design was to charge a battery from a solar panel. So with this, we needed some sort of smart circuit that doesn't overcharge the battery and keep monitoring the battery every time. For this, we used MCP 7333 IC chip. This does exactly what we needed to do, that monitors the battery all the time, and it also has the ability to program the current going into the battery. So let's say if you're using a bigger solar panel and you want to charge your battery faster, you can program the current going into the battery by just replacing a resistor that I will explain better in the next circuit. So this is our whole circuit of just charging the lithium battery in there. Right here, as I talked about the programmable resistor, 4.7, right now we're using 4.7 because from our solar panel, we are getting about 200 to 300 milliamp hour of current. And with this, we are having 200 milliamp going into the battery. So if you are using a bigger solar panel, let's say, that provides 400 or 500 milliamp, so you can simply reduce this resistor to 2.2 and have it to 500 milliamp going into the battery. And as you can see in my circuit, there are 3 LEDs. These are for user to let know what their circuit is doing. Like in this LED lights up when you're out in the sun, and it just tells you that there is a power. Now you can charge your battery. And this LED, it reduces and gets brighter and gets less brighter depending on how much light is present. So if you're out in bright sun and this LED is totally lit, right, same as this one, so it can just give you an idea like where to put your charger, like where it will be charging the fastest. And the third LED just lights up and it tells you that your battery is fully charged. Now you can take the charger. And this is just a simple flow chart explaining how everything goes. And next thing was, like he explained earlier, since we are charging a 3.7 volt battery, but all the cell phones and other products, they need 5 volts to charge. And for this, we needed a voltage booster. And for that, we needed to come up with something that does not consume much of the electric power of the battery. For this, we used MAX 756 chip. The reason why we're using this chip, it gives us 5 volt step-up converter, plus it does not take as much power. And also we were concerned about like whether to put a switch or not, when to boost the voltage to charge or not. Since the standby power consumption for this is very low, it only takes 60 microamp current. So our battery is 1200 milliamp hour. So it's gonna, in a standby mode when you're not charging anything, it's gonna take this chip 20,000 hours to completely take juice of the power from the battery, which is 2.28 years. So we didn't need any kind of switch put in there. And here is just a circuit that boosts up to 5 volts. And as you can see in this graph, our battery is 3.7 volt battery. So at 3.3, you are getting almost 86% efficiency. And with this, we are getting 90% with 3.7. So we are only losing 10% of the battery just to boost it up. And next thing was, like, today it's clouds outside. There is not enough sun, so it's not enough to charge your phone. As we were thinking about just completely and different alternative for a wall charger, so we needed to include something for backup for days like today. Well, there is no sun, so we needed some sort of backup to charge your phone if you want to keep it as a permanent device. And for that, we needed to, again, same thing, like we don't want to use something that consumes too much power. So we decided to go with the ICL 763 chip. Basically, what this does, this has one primary source of input, one secondary source of input. So it basically monitors both batteries, and it sees when the primary source battery is dead, it automatically, instantly switches to the backup battery, and also turns on this LED to let the user know that now you are on your backup battery. And while we were deciding which backup battery to use for, like in our preliminary design, we went with 9 volt battery. But then we found out by doing more research and doing some calculation that the 9 volt batteries actually, we need 5 volts for our project. We are losing 4 volts and 0.4 watt hour by using 9 volt battery. But just using 2 AA batteries, we are getting more power compared to the 9 volt battery. And it's AA batteries are available everywhere. People can buy them. They are inexpensive compared to the 9 volt battery. So we went with 2 AA batteries. And also, like he explained earlier, that we needed a display the charge on an LCD, like how much battery is left on your charger and how long it's going to take out in the sun to charge the battery. We use PIC microcontroller to do that. The reason why we use PIC is because of its compact size, and also it does not consume much of the, it consumes very less electricity, and it runs on a low voltage, which was perfect for our design. And here's a circuit that we have to display everything on the LCD. We have a microcontroller connected to the LCD that sends the signal from this battery. And we have a push switch over there. So this LCD is not running all the time. It only will show you the display of a battery left and how much time left only when you press the button. So we have a button on it. When you press it, it shows you how much battery is left and how long it's going to take out in the sun. Here's the whole design of all the circuits connected together to each other. This is our battery charger circuit. That's the microcontroller, the LCD, battery switching, and a voltage booster. And I'm going to move on to Mr. Harris. He's going to explain more about our prototyping.
Good afternoon. When we started our circuit, we started using a breadboard like everybody else to test out all the components and all the circuits. And once we realized everything is working fine, we went on and we started doing the prototyping for our design. We used a vector board initially to design. You can see all the components are up in the front, and the wiring and all the colors are all at the bottom. From there on, we also decided to do the PCB design. The PCB design, we use two different software. We use Eagle software and a PCB Artist. Our major product, the final product, is going to be a PCB. That's the reason why we use it, because it's more cleaner, compact, and it's a smaller size and much user-friendly. Here are some of the pictures of our complete product. As you can see right here, this is the box. It's a raw box right now, but there are some LEDs here, and the solar panel is at a certain angle to get the maximum input from there. This is the other angle of this the box where you can see all the components in there. This is showing where the PCB is connected with the solar panel, and the phone is actually charging, which is the sole purpose of our project. Right here you can see. This is a view in the car. This is on the dashboard. The reason why we show this picture is because if you're going at work, you're going somewhere where you're working at an 8-hour shift, you can leave your charger in the car during the day while it charges the whole entire time. So if you want to use your phone or your other electronics at night, you have the lithium polymer battery completely topped up by the time you get back. There's a video that we're going to show, a demo for our project. Over here, you see that we're showing the intensity. Right here, when it covers up, the LED goes off. That shows us the intensity of the LED. Right here, the push button is showing the LCD screen where it turns on and tells you the charge on the battery and tells you the estimated time it requires. And this is where the phone is being connected. This is the outdoor where the phone is being connected. And right here, you can see the charge on the battery coming up. Right here, it's charging. Our second option, second situation is indoors. This is where the solar panel is basically useless, but the lithium polymer battery still charges the phone. And right here you can see it still charges the phone. Over here you're going to see we're going to switch the lithium polymer battery to the backup battery. And when we do that switch, you're going to see the yellow LED turn on that tells you that the backup battery kicks in right here. And then even though the backup battery is still kicked in, the phone is still charging at the same time. So there's not going to be any time when your phone is not going to be charging. So even if the lithium polymer battery runs out of charge, you'll still have your backup battery kick in. These are some of the results that we took. Over here at the top, you can see the solar cell and sunlight solar cell at the bottom in the rainy day. The reason why I'm showing you this, that this right here, 45-degree angle, is with our test we found out this is the most optimal angle for solar cell to generate the maximum voltage and maximum current that we require. Right here, these are different conditions and different locations that we tested our product in. As you can see, right here in the rainy weather, the current isn't ample enough. This is the problem that we ran into in our preliminary design. This is where, in this situation, is where the backup battery kicks in. All the rest of the situations, the lithium polymer battery can take care of it. Some of the products that we tested out, the daily use products that you guys have, the GPS, the iPods, the iPhone, different cell phones, cameras. These are just showing the time it takes for, such as an iPod to charge. It takes about 1.5 hours to charge. And with the topped up lithium polymer battery, you don't need to charge your lithium polymer battery the whole entire time. When it's topped up, you can charge your iPod Nano 3 times. To give you an idea, an iPod lasts you about 8 hours, so you can keep the battery running at that time.
All right, the total funds we spent on this project were around $415. This is because we tested different solar cells, we tested different kind of circuits, everything to make sure that nothing overcharges anything and everything stays durable and consistent for every consumer. We made two kind of models for all of you. One model, you got an LCD and a microcontroller, you got a big solar cell. This thing will charge your whatever you want in about 6 hours, approximately. Now, this thing, we're making it around, putting all costs together around 55. And a basic model, basically we're talking no LCD, no microcontroller, but you still get the backup battery. Smaller solar cell, it'll take twice as long to charge, but it's only $23 approximately, and I'll cut everyone a 10% discount if you want. These are the individual contributions we had to the project, and these are the man hours we worked. Most of the man hours might look a little smaller compared to most of the other projects. That's because this project, we had to switch gears very quickly because we started off with a whole different design and we ended off with a whole different one. Same concept, just a different build to it. The lessons we learned were microcontroller implementation. None of us were CPEs. We went from scratch. We learned how to do a printed circuit board implementation in a good way. We learned about solar technology, how well they are, how efficient they are, and also how project design teamwork works, basically who does what, how it goes, leadership, who's better at what, make sure no one gets too much load or anything. But that wraps up our presentation. Are there any questions that you guys might have for us?